Space is vast, it's full of incredible objects, and one of the most fascinating is the black hole. Imagine a place where gravity is so strong, nothing escapes, not even light. That's a black hole. Black holes sound like science fiction, but they're real, scattered throughout the universe. Astronomers are finding new ones all the time. Studying them helps us understand the universe's biggest secrets. Black holes come in different sizes. Some are small, just a few times heavier than our sun, while others are supermassive. Giants that are millions or even billions of times heavier than the sun. Black holes are mysterious and powerful, pushing the limits of our understanding. Let's journey into the heart of a black hole. We'll see how these cosmic abysses work and why they're so important. Gravity is everywhere. It's an invisible force that shapes the universe. It holds us to the Earth and keeps the Earth orbiting the sun, maintaining the delicate balance of our solar system. Gravity is a force of attraction between anything with mass. It's what pulls objects towards each other. The more massive an object, the stronger its gravity. This is why planets and stars have such powerful gravitational pulls. Black holes form when gravity becomes extreme, reaching levels that are almost unimaginable. Imagine a star much more massive than our sun, a giant in the cosmic landscape. As it runs out of fuel, it can no longer support its own weight. The balance between gravity and internal pressure is lost. The core collapses in on itself, a dramatic and violent process. The gravity becomes so strong that nothing can stop it. Not even light can escape its pull. This collapse crushes the star's core, squeezing the matter into an infinitely small point called a singularity, the heart of a black hole. It's a point where density becomes infinite. The singularity's gravity is off the charts, warping the fabric of space and time around it. This warping effect is so intense that it bends light and distorts reality. This warping is so extreme that it creates a region of no escape, which is what we call a black hole. It's a cosmic trapdoor, a place where the known laws of physics break down. Stars are like cosmic furnaces, burning bright, fueled by nuclear fusion in their cores. This fusion creates outward pressure, balancing the inward pull of gravity. Massive stars live fast and die young, burning through their fuel quickly. When the fuel runs out, the outward pressure stops and gravity takes over. The star's core collapses rapidly, triggering a supernova explosion. The outer layers of the star are blasted into space, an explosion that can outshine an entire galaxy. Meanwhile, the core continues to collapse. If the core is massive enough, it forms a black hole, sitting silently in the remnants of the supernova. It's a cosmic tombstone for a once mighty star. Singularities are mind-boggling. They're points of infinite density, where all the matter from the collapsed star is crushed into an infinitely small space. Our current laws of physics break down at a singularity. We can't explain what happens inside. It's like dividing by zero on a calculator. You get an error message. Some theories suggest that singularities might be gateways to other universes, or they might lead to the creation of new universes. The singularity is a cosmic mystery, a place where our understanding of the universe reaches its limits. Imagine approaching a black hole. As you get closer, you'd feel gravity pulling you in, but there's a point of no return. This point is called the event horizon. Cross the event horizon, and you're trapped forever. Not even light can escape the black hole's gravity from within the event horizon. This is why black holes appear black. The event horizon isn't a physical boundary. It's a region of space-time where gravity is so strong that all paths lead inwards. It's like being caught in a cosmic drain, spiraling towards the singularity. The size of the event horizon depends on the black hole's mass. A black hole with the mass of our sun would have an event horizon with a radius of only about 3 kilometers. Black holes are famous for their insatiable appetites. They gobble up anything that gets too close, from stars to entire planets. But even black holes can't eat forever. Surprisingly, they can also lose weight. Over time, they actually lose a tiny bit of mass, a process that might seem counterintuitive. This slow weight loss is due to a fascinating phenomenon called Hawking radiation, named after the brilliant physicist Stephen Hawking, who first proposed its existence in 1974. Hawking radiation is a quantum effect, rooted in the strange and mysterious world of quantum mechanics. It occurs at the event horizon, the boundary beyond which nothing can escape the black hole's pull. Tiny particles are constantly popping in and out of existence near the event horizon due to quantum fluctuations. Usually, these particles annihilate each other almost instantly. But sometimes one particle falls into the black hole while the other particle escapes into space. This escaping particle carries away a tiny bit of the black hole's energy and mass, leading to a gradual loss over time. Hawking radiation is incredibly faint, almost imperceptible. It's so weak that it's currently beyond our technological capabilities to detect directly. However, despite its faintness, it plays a crucial role in the long-term evolution of black holes, potentially leading to their eventual evaporation over astronomical timescales. Most galaxies, including our own Milky Way, harbor a secret at their centers: supermassive black holes. These behemoths are millions or even billions of times more massive than our Sun. Supermassive black holes are engines of galactic evolution. Their gravity influences the orbits of stars and gas clouds within the galaxy. We're not sure how these giants form. One possibility is that they grow by merging with other black holes. Another idea is that they form from the collapse of massive gas clouds in the early universe. Supermassive black holes can be surprisingly active. They can pull in surrounding gas and dust. This material forms a swirling disk around the black hole, called an accretion disk. As material falls into a supermassive black hole's accretion disk, it heats up to incredible temperatures. This superheated material emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. These active supermassive black holes are called quasars, short for quasi-stellar radio sources. They are some of the most luminous objects in the universe. Quasars are so bright that they can outshine their entire host galaxy. They are like cosmic lighthouses, visible from billions of light years away. Studying quasars helps us understand the early universe. They provide insights into the formation and evolution of galaxies. They also offer clues about the nature of gravity and the extreme conditions near supermassive black holes. When massive objects like black holes collide, they create ripples in the fabric of space-time. Much like a stone thrown into a pond creates waves. These ripples are called gravitational waves, and they carry with them the energy and information from the cataclysmic events that caused them. They travel at the speed of light, traversing vast distances across the universe, bringing with them clues about the nature of the cosmos. Albert Einstein predicted the existence of gravitational waves in 1916 as part of his general theory of relativity. However, it wasn't until 2015, nearly a century later, that scientists finally detected these elusive waves using advanced instruments. This groundbreaking discovery marked a monumental milestone in space exploration, opening a new window into the universe and allowing us to observe cosmic events in a completely new way. The first gravitational waves detected came from the merger of two black holes about 1.3 billion light-years away, a truly staggering distance. Since that historic detection, astronomers have identified dozens of gravitational wave events, with most of them originating from black hole mergers. Gravitational wave astronomy is still in its infancy, but it holds immense promise for the future. This new field has the potential to revolutionize our understanding of the cosmos, offering insights into phenomena that were previously beyond our reach. By studying gravitational waves, we can investigate objects and events that are invisible to traditional telescopes, such as black holes and neutron star collisions, providing a more complete picture of the universe. Black holes play a role in the fate of the universe. As they continue to grow and merge, they will eventually consume most of the matter in the universe. But even black holes don't last forever. As we discussed earlier, they slowly evaporate through Hawking radiation. This process takes an extraordinarily long time, much longer than the current age of the universe. In the far distant future, when all the stars have burned out and galaxies have drifted apart, black holes will be the last remaining objects. And eventually, even they will disappear, leaving behind a vast, cold, and empty universe. The study of black holes forces us to confront the ultimate fate of the universe. It reminds us that even the most powerful and long-lived objects are not eternal. Black holes are more than just cosmic oddities. They are natural laboratories for studying the fundamental laws of physics. They push our understanding of gravity, space-time, and the nature of reality itself. By studying black holes, we gain insights into the evolution of stars and galaxies, the behavior of matter and energy under extreme conditions, the origin and fate of the universe. Black holes challenge us to think differently about the cosmos. They force us to question our assumptions and expand our horizons. The quest to understand black holes is a journey into the unknown. It's a journey that continues to inspire awe and wonder. And it's a journey that will undoubtedly lead to new discoveries and a deeper understanding of our place in the universe.